In this video, we're going to work with Chapter 4, Sections 1 and 2 in Honors Geometry. And before you start watching this video, please make sure that you have read through Chapter 4, Section 1 in your textbook. If you have not, please pause the video and read through that section on how to classify triangles. If you have already finished that, please pause the video and do the first 4 slides on your PowerPoint. Once you have finished those 4, please restart the video or unpause the video, and we'll go through the results of that. So, in the first part of this, we're going to look at classifications of triangles by sides and by angle measures. By angle measures, we can classify a triangle as acute, right, obtuse, or equiangular. By side length, we can classify a triangle as equilateral, isosceles, or scalene. In this first do now problem, we're going to write an algebraic equation to find the value for x. So writing that algebraic equation based on what was given to us with the tick marks gives us a value for x of 8.5. Once I have that value of x for 8.5, I can plug that in and find the 3 side lengths of the triangle. So side JK has a length of 23.3, so does side KL, and then side JL has a length of 44.5. In the next problem, I'm told that my triangle is equilateral, so all 3 segments are congruent. I can choose any of the 2 as equal segments to be able to solve for the value for y. This one happens to use segments FG and GH being equal in measure, so 3y minus 4 equal to 2y plus 3. But I also could have solved 2y plus 3 equal to 5y minus 18, or 3y minus 4 equal to 5y minus 18. All of them would have given me the value for y equal to 7. Once I know what the value for y is, once I plug it back in, I'll find out that FG, GH, and FH all have a segment length of 17 units, as expected because we were told that the triangle is equilateral. In the next problem, we're trying to figure out how many triangles can be made out of a 424-foot piece of steel beam. Since each triangle is 18 feet on a side, the perimeter of each triangle is going to be 54 feet. So, how many 54-foot long triangles can fit into a 424-foot piece of steel beam requires some division. And that will give me 7, but not quite 8 triangles that I can form out of that 424-foot piece of steel. So 7 and 7/9 triangles I can find, so realistically I can form 7 triangles, but not the 8th. Last piece here, classifying the triangles by both angle measures and by side measures, gives me triangle MNQ, triangle NQP, triangle MNP, as seen in the slide here. And for number 4, finding the side lengths of the triangle, we're going to set 3x plus 2 equal to 4x minus 7. That will give us an x value of 9, which then plugging it back in gives us 3 sides of lengths 29, 29, and 23. So, now we're ready to move on to section 2, which works with the measures of the interior and exterior angles of triangles and proves some theorems about those triangles. So we're going to start with the long-awaited triangle sum theorem, which states that for any triangle, the sum of the measures of the 3 angles of that triangle is 180 degrees. So in other words, for the triangle ABC that's shown here, the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180 degrees. In order to prove this theorem, we're going to add an auxiliary line to our diagram. And as we talked about already, an auxiliary line is a line that can be added to a diagram, added to a figure to help us out to prove something. Now, auxiliary lines can only do 2 things, And the auxiliary line that we're going to add to our diagram here is going to do two things. It's going to go through point B, and it's going to be parallel to the line AC. This line is guaranteed by Euclid's parallel postulate, which says that through a point not on a line, exactly one line parallel to my given line can be drawn. So I'm going to draw through point B, one line parallel to the line AC. So that's what I'm going to draw with my auxiliary line here. So this is the line that's used in the triangle sum theorem. So here goes the proof. Once I take my diagram with triangle ABC here, I want to be able to prove that the measures of 1, 2, and 3 add up to 180 degrees. The only thing I have to start with is the fact that I have a triangle, so I'm going to add in that auxiliary line through point B, parallel to line AC, and my reason for that, as I stated earlier, is Euclid's parallel postulate. Now, once I have that line drawn in here, I can use my parallel lines to find a couple of pairs of angles that are congruent, and those are going to help me prove this theorem. The other thing that's going to help me prove this theorem, if you look at the diagram up at point B, you'll notice that we have a couple of angles up there that will all add up to 180 degrees. So, here's what we're going to do is to take our parallel lines and first of all be able to state that we've got a couple of pairs of congruent angles. Angles 4 and 1 are congruent, as well as angles 5 and 3 are congruent because of PAI. The lines are parallel, they're both pairs of alternate interior angles, so we've got congruent angle pairs there. Since I'm going to be using some substitution a little bit later, I'm going to convert those into equality of measure using the definition of congruent angles. But then it's up at the top of the diagram, up at point B, that I'm going to get my other piece of information. I can see, looking at my diagram, that the measures of angles 4, 2, and 5 all add up to 180 degrees. And that just comes from the angle addition postulate. Those three angles together make up the straight angle, so their measures add up to 180 degrees. And once I have that, if I substitute the measure of 4 in the place of 1, if I substitute the measure of 5, substitute that for the measure of angle 3, I can take my statement in 5 and rewrite it to state that the measures of those three angles add up to 180 degrees. And there's the proof of the triangle sum theorem. Now, there are a couple of corollaries that follow from the triangle sum theorem, and corollaries are kind of like baby theorems whose proofs are so closely linked to a big main theorem like the triangle sum theorem that that we don't really have to prove too much to be able to get to see that they're true. So here are a couple of corollaries that go along with the triangle sum theorem. The first one here says that the acute angles of a right triangle are complementary. Well, here's the thought process. The three angles have to add up to 180 degrees, and if angle F is a right angle, its measure is 90, which means we've got 90 degrees left to split between the measures of D and E, which means they're going to add up to 90 degrees together, which means they're complementary. The other one that follows directly from this is the fact that the measure of each angle of an equiangular triangle is 60 degrees. And here's the thought process with that one. If the three angles of a triangle add up to 180 degrees, and all three angles are congruent, which is what is meant by an equiangular triangle, then their measures are all equal. So I've got three angle measures that are all the same that add up to 180 degrees, which means they're going to be 60 degrees each. We're going to skip now over to a couple pages through in the PowerPoint, which talks about interior and exterior points in a triangle. And the interior of a triangle is inside the triangle's walls, the triangle's boundaries, and the exterior of a triangle is the set of all points that are on the outside. So the interior, the exterior of the triangle. An interior angle is one of the angles inside the figure. So angles 1, angle 2, angle 3 are formed by two sides of the figure. Those are all interior angles. An exterior angle is an angle that's formed by one side of the triangle and an extension of an adjacent side. So angle 4 is an exterior angle to the triangle. It's an extension of the side that joins angles 1 to 3. So we've taken and extended one side of the triangle and we've created angle 4. Angle 3 is the interior angle. Angle 4 is the exterior angle that goes with it. Each exterior angle has two what are known as remote interior angles that are associated with it. A remote interior angle is an angle that's not adjacent to the exterior angle. So 3 and 4 are adjacent. Angle 4 is not adjacent to either angle 2 or angle 1, which means both angles 1 and 2 are remote interior angles to angle 4. Remote, removed from, away from, so that's what angles 1 and 2 are. These are used in what's known as the exterior angle theorem, which says that the measure of the exterior angle of a triangle, like angle 4, is equal to the sum of the measures of its two remote interior angles, in this case angles 1 and 2. So the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2. And we're going to prove it next. So we're given the triangle with the exterior angle at angle 4. We're trying to prove that the measures of 1, 2, and 4 are equal to, the measures of 1 and 2 are equal to the measures of 4. I do know with the triangle sum theorem that the measures of 1, 2, and 3 add up to 180 degrees. And I can also see a linear pair over here with angles 3 and 4, which means I know that angles 3 and 4 are supplementary, and therefore their measures add up to 180 degrees as well, with the definition of supplementary angles. Both 180s here will mean that the measures of 1, 2, and 3 will add up to the same thing as the measures of 3 and 4 with a little bit of substitution of equality. And if I notice that I have the measure of 3 on both sides here, a little reflexive property of equality will allow me then to subtract out the measure of 3 from both sides and be left with the measure of 1 plus the measure of 2 equal to the measure of 4 with the subtraction property of equality, which is what we were trying to prove. So there's the proof of the exterior angle theorem. Skipping over again a couple of slides to the last theorem in this section, the third angles theorem. This one says that if two angles of a triangle are congruent to two angles of another triangle, then those third angles, hence the third angles theorem, are congruent. So for example, if angles L and R are congruent angles, the same size, angles M and S are congruent angles, the same size, then that leaves nowhere to go for angles N and T but to be congruent angles as well. And we're going to finish off this video with the proof of that. So, we've given two pairs of congruent angles between the triangles, which is going to mean that in triangle LMN, the three angles add up to 180 degrees, and in triangle RST, the three angles also add up to 180 degrees, both by the triangle sum theorem. Both add up to 180, which means the measures of L, M, and N add up to the same thing as the measures of R, S, and T with a little bit of substitution. Using the fact that the R angles were congruent, I can say that the measures of L and R are the same with the definition of congruent angles, so that I can subtract out their measures from both sides to be left with the measures of M and N equal to the measures of S and T. I'll do the same thing with the measures of M and S, since they were congruent angles given to me, and I'll subtract out their measures to be left with the measures of N and T equal, by subtraction property of equality again. Equal measures means congruent angles, so I'm going to finish this off with the definition of congruent angles. And that's the video for Chapter 4, Sections 1 and 2. Now that you've completed and written down these proofs, what I'd like you to do is to go ahead and try the problems that apply these in the PowerPoint. And our next video will check the answers to those. Thank you.